Cool. Hello, Professor Wang. This is Jeff and Stefan. We worked together on Project One, and here's our video portion of our submission, take 3. So we started with the initial differential equation that was given with acceleration. We integrated it once and to find velocity, and then to find our constant of integration, we set v of t equal to 0 because at time 0, the velocity is 0 because it's when it's let go and free fall. And so that meant that the first constant was 0. Then we integrated again to find h of t, and we knew also to find this constant of integration that the height at time 0 would be just the initial height. So we're calling that h naught, and in the case of the cone, it is the height when the cone is full of water, which is a given. So we were then able to set our h of t equation equal to 0. So when height was equal to 0, that would be the time, and then solving for t, that would be the time when the object hits the ground, or in the case of the cone, when it's totally empty. So we were able to find a time and then plug that back into our velocity equation. And then we found that the velocity would be equal to minus root 2 gh naught, which makes loads of sense. And it's also exactly what it was supposed to be. So that's helpful.
Moving on to B, we realized that in order to take the integral to get the equation shown in part 4 that says Torricelli's law, we need to have r in terms of h. So we set up a ratio where, as you can see on this third line, r equals h times r naught over h naught, which is essentially the radius of the tank, the height of the tank, in relation to the radius of the water and the height of the water. So we're able to express radius in terms of h, which was crucial for our integrals. And we get our volume equation, the volume of a cone, 1/3 pi times h, which is now, it used to be r squared, which is now h times r naught over h naught squared times h. Simplify it out, and then we take the derivative to get volume with respect to height, but then realize that the equation requires the volume with respect to time. So we multiplied both sides of the dv dh by dh dt to get dv dt. So volume in terms of time, and that our equation, pi times r naught over h naught squared, h squared dh dt, we were able to get for our equation.
So in part C, we were tasked with finding the finding a height equation for the, or height with respect to time as height changed with time as the cone flows out. So what we did is we had dh dt, and using separation of variables, we were able to integrate. And to find this constant of integration, we knew that when time was equal to 0, that it would be the total height of the cone. But we were not given the total height of the cone. We were given the height of the cone to the point where it was chopped off so that the water could come out. So we called the rest of that, imaginary cone B, and created another ratio between the radius of that small, imaginary bit of the cone. That was 0.5 centimeters, which was a given. So 0.5 over b was equal to 30 centimeters, which was the radius of the overall cone, divided by that height, which was 50 centimeters as a given, plus b, that little extra bit. And so we were able to find a b and then plug in h naught plus b as our initial condition for h of 0 equals h naught plus b. We were then able to solve for c and find a constant of integration. And then we just use that constant of integration to have our height function. And we also were able to find the area of the small, the opening. Just, we knew the radius, so we were able to do it as pi r squared. And so pi r squared in this case is just pi over 4.
Then part D asked us to calculate the time it took for the tank to fully empty itself. That condition is when h of t equals 0, so the height of the water is now 0. And we, in order to make it easier to solve for t, we use the equation from C, this second line here, 2/5 h to the 5/2, with our constant of integration already calculated in there, as Stefan just went over. So doing that, the left side cancels out to 0. We're able to solve for t, and then plugging in our initial conditions, 30 centimeters, 50 centimeters. And then our g, for our gravity constant, we have to convert to centimeters per second squared. So that just becomes 980.7. Plugging all in the numbers, we get 239.8 seconds for our time.
So part E flipped the problem on its head. I can't believe I've made that joke 3 times now. So we basically went back to part B, to square 2, I guess, and redid our integral. But instead, this time, because the height, the cone is flipped over, and the heights are a little bit different. So we were able to substitute and rename h to h naught, so the total height, minus h. And that took into account the cone being flipped over and how it would be draining a little bit differently. We then redid the integral pretty much the same way that we had in parts B, C, and D, and found a different constant of integration that instead of being 2/5 was 16 over 15, and then the rest of it was the same. And plugged that in, and were then able to find a t again as 613 seconds after plugging in all of our initial conditions, and the same as before. And we saw that it was bigger and sort of thought that, okay, why does this make sense that it's slower? Not only because you had mentioned that to us in class that it would be, but there's less, as the cone gets wider as it goes down, there's less weight on top pushing it down, which does make sense. And also, then in terms of the number itself, we looked at the ratio between our coefficients in front of the h naught to the 5/2, because that was the only part that changed from one equation to the next, from D to E. So we looked at the ratio of those. So 16 over 15 to 2/5 is 2.6, and which is the same as the ratio between time 2 and time 1. So time 2 is 613 seconds, time 1 was 239.8 seconds, and the ratio between those two is also 2.6. So based upon those metrics, we feel confident that our numbers make sense. So yeah.
Yeah, and I'd like to point out the way we got that constant of integration for part E. We use the condition that at time of 0, so h of 0 equals h naught. So when the time first starts, meaning the water is full, the tank is full, that we were able to substitute h for h naught in order to find that constant of integration. So that's why we get rid of all the h's and replace them with h naught. Great. Anything else?
I don't think so.
Thanks.
Don't go yet. This is Jeff again. We slightly changed our answer to part E. So what was reflected in the previous video for the last page doesn't actually reflect our final answer. We, in short, forgot to add in B, meaning the rest of the cone that was chopped off. So when we were calculating our constant of integration, instead of doing h naught, we instead did h naught plus B, just like we did, I think that was in part C. So our final answer is not what was shown in the video, but it is shown on the PDF attached. Thank you so much.